Welcome to the full video lecture on common distributions. The content covered in this video can be found in the Lock 5 textbook in Chapter 5 and in sections P.4 and P.5. Chapter P can be found at the end of your textbook. The full video lectures can get long, so I recommend that you do not watch this video in its entirety all at once. Instead, between learning objectives, you should take breaks to look at the textbook or the online notes, or to try a few practice problems in Wiley+. For each of the learning objectives, I'll let you know which section of the textbook they come from. That way you can find appropriate questions in Wiley+. Over the last few lessons, you've approximated sampling distributions using bootstrapping and randomization methods. You may have noticed that many of the distributions that you have constructed look similar to these. These are all similar to a normal distribution. This phenomenon is known as the central limit theorem. We'll learn more about this later in this video. In this lesson, we're going to learn how many sampling distributions can be approximated using a normal distribution. At the end of the lesson, you'll also be introduced to the binomial distribution, which can be used in cases with proportions where the central limit theorem can't be applied. Let's start now by reviewing our learning objectives for the week. There are 5 learning objectives for this lesson. The first 3 learning objectives are related to normal distributions. The last 2 learning objectives are related to binomial distributions. We'll start now with the first learning objective. Find the area under a normal distribution using Minitab Express and StatKey. This content is introduced in the Lock 5 textbook in section P.5. It's also reviewed at the beginning of section 5.1. This is a normal distribution. Theoretically, a normal distribution is continuous and may be depicted as a density curve, such as this one. This is a special type of normal distribution. It has a mean of 0 and a standard deviation of 1. This is a standard normal distribution, also known as a z-distribution. You may see the notation n, and then in parentheses mu, comma, sigma. N signifies that this is a normal distribution, mu is your population mean, and sigma is your population standard deviation. For a z-distribution, you may see n, 0, 1. In other words, a normal distribution with a mean of 0 and a standard deviation of 1. While we cannot determine the probability for any one given z value, because this distribution is continuous, we can determine the probability for a given interval or range of values. The probability for a range of values is equal to the area under this density curve. The total area under this curve is 1, or 100%. In other words, 100% of observations fall under the curve. In previous lessons, you've used the standard error method to construct confidence intervals. This is one application of a normal distribution. When you constructed a 95% confidence interval, you used a multiplier of 2, because approximately 95% of the normal distribution falls between z-scores of -2 and +2. Here's a distribution plot that I made using Minitab Express that separates the middle 95% from the outer 5%. Here we can see that the actual z-scores are negative and positive 1.95996. The empirical rule rounds this to plus and minus 2. Before we move on to showing you how to construct these distributions in Minitab Express and StatKey, there are a few things that I'd like to review. First, this is the empirical rule. Recall from earlier lessons that the empirical rule can be used to estimate the proportion of observations that should fall within 1, 2, and 3 standard deviations of the mean on a normal distribution. Let's look at an example. IQ scores have a mean of 100 and a standard deviation of 15. Apply the empirical rule to find the IQ scores that separate the middle 68%, 95%, and 99.7%. The middle 68% of scores will fall within 1 standard deviation of the mean. In other words, 100 plus and minus 1 times 15. This gives us a range of 85 to 115. The middle 95% of scores will fall within 2 standard deviations of the mean. 100 plus and minus 2 times 15 gives us a range of 70 to 130. The middle 99.7% of scores will fall within 3 standard deviations of the mean. 100 plus and minus 3 times 15 gives us a range of 55 to 145. Next, I want to review z-scores. A z-score is a standardized score. It tells you where that one observation lies in relationship to the mean in standard deviation units. This formula should look familiar from earlier lessons. This can also be rewritten in terms of population parameters. Here, the mean is changed to mu and the standard deviation is changed to sigma. Note, however, that these are the same formulas. Using a bit of algebra, we could also solve for x. In doing so, we can transform a score on a z-distribution to any other normal distribution with a mean of mu and a standard deviation of sigma. Next, I'm going to take you to Minitab Express to show you how to construct these probability plots. We'll use Minitab Express to construct z-distributions to find the area that is less than 1, greater than 1, between -1 and +1, and beyond -1 and +1. I'm in Minitab Express with a blank worksheet. We don't need any data to make these probability plots. I'm on a Mac, so I'm going to go to Statistics, Probability Distributions, Distribution Plot. If you're on a PC, you'll just have to go to Statistics, Distribution Plot. I want to display a probability. The default in Minitab Express is a z-distribution. In other words, a normal distribution with a mean of 0 and a standard deviation of 1. The first example that I want to show you is how to find the area that is less than a z-score of 1. So I do not have a probability, I'm looking for a probability. I have a specified x value. And I want to find the area that's less than 1, so that would be a left-tailed probability. After I enter 1, I'll click OK, and Minitab Express will give me my distribution plot. At the top, we can confirm that we have a z-distribution. It's a normal distribution with a mean of 0 and a standard deviation of 1. On this plot, we can see that we're looking at the area less than a score of 1. This red shaded in region is 0.841345. In other words, 84.1345% of this distribution is less than 1. Next, let's find the area that's greater than 1. Again, I'll go to Statistics to construct a distribution plot. I want to display a probability. We're using the default standard normal distribution. I have a specified x value, and I want to find the area greater than, or to the right, of 1. The area on this distribution to the right of 1 is 0.158655. Next, let's find the area that's between -1 and +1. Again, I'll go to Statistics to construct a distribution plot. To display probability, I have specified x values. I want to find the area in the middle, between -1 and and positive 1. The area on a standard normal distribution between -1 and positive 1 is 0.682689. Last, I want to show you how to find the area that is less than -1 or greater than positive 1. Go to Statistics, Distribution Plot, Display Probability. I have specified X values, but this time I want to find the area in the tails, and I have equal tails. Here I could either type -1 or positive 1, because Minitab Express is looking at equal tails, so it's going to mirror that. Note that when Minitab Express gives you these proportions, it gives you the proportion each tail separately. So to find the total area that's shaded in, we'll have to add these together. 0.158655 plus 0.158655 gives us a total shaded in area of 0.31731. These examples all used a standard normal distribution. In Minitab Express, you can change the mean and the standard deviation to any values. Let's look at one example of this. Let's say that we're looking at IQ scores. Recall, IQ scores are normal with a mean of 100 and a standard deviation of 15. Maybe we want to know what proportion of IQ scores are greater than 110. So we have a specified X value of 110, and we want to know the proportion of scores that are greater than this value, or in the right tail. Here, Minitab Express has constructed a normal distribution for us with a mean of 100 and a standard deviation of 15. It's shaded in the area that is greater than 110. In other words, we can say that 25.2493% of IQ scores are greater than 110. In all of these examples, we've had a specified X value. It's also possible to tell Minitab Express a proportion to find the z-scores or scores on any other normal scale that separate given proportions. For example, let's find the z-scores that separate the middle 95% of observations from the outer 5% of observations. In other words, the multiplier that we would use when constructing a 95% confidence interval. Again, we'll go to Statistics to construct a distribution plot and display probability. This time we do have a specified probability. We have 95% in the middle and 5% split between the left and right tails. We have equal tails, and we see here that the value that we're reading in is P, where P is evenly split between the left and the right. So 5%, or 0.05, are evenly split between left and right. The z-scores that separate the middle 95% from the outer 5% are plus and minus 1.95996, which we saw earlier, and the empirical rule rounds to 2. Let's find the z-scores that separate the middle 90% from the outer 10%. Again, we'll construct a distribution plot to display probabilities. We have a specified probability, and we have equal tails. We have 90% in the middle and 10% split evenly between the left and the right. The z-scores that separate the middle 90% of observations from the outer 10% are plus and minus 1.64485. Like before, we don't need to have a standard normal distribution. We could look at any normal distribution. Let's look at IQ scores next. Again, we'll construct a distribution plot to display probabilities. IQ scores are normal with a mean of 100 and a standard deviation of 15. Maybe we want to know what IQ is the cutoff for the 90th percentile. So the 90th percentile would be the value where 90% or 0.90 fall to the left and 10% or 0.10 fall to the right. The IQ score for the 90th percentile is 119.223. There are more examples of using Minitab Express to construct these distribution plots, given both z-scores and proportions in the online notes. If you're looking for more practice, I suggest that you go through there to work through more examples. Everything that we just did in Minitab Express can also be done in StatKey. Let's go to StatKey next to walk through a few examples there. In StatKey, we're going to be looking at a theoretical distribution, and that is the normal distribution. Just like in Minitab Express, the default in StatKey is a standard normal distribution, in other words, a z-distribution, with a mean of 0 and a standard deviation of 1. You can edit these parameters in StatKey. For example, if we wanted to look at IQ scores with a mean of 100 and a standard deviation of 15, we could do that. For this example, though, let's start with a standard normal distribution with a mean of 0 and a standard deviation of 1. At the upper left of this distribution, we have the options for left tail, two tail, and right tail. We'll start with a left tail example, just like we did in Minitab Express. Now the default in StatKey is always to give you 5% in the tails, which is evenly distributed with 2.5 on each side. The first example that we did in Minitab Express, we found the proportion of the normal distribution that was less than z equals 1. Let's do that again here. So we're looking for a proportion less than a given value, so it's a left-tailed test. We can click this value at the bottom to change it to positive 1. Now we can see that the area that is less than z equals 1 is 0.841. Next, let's find the area that's greater than z equals 1. We'll get rid of that left tail that we just worked with, and now we have a right tail probability. Again, the default is to put 2.5% in each tail. We can change this number at the bottom to 1 so that we can find the area under the curve that is greater than z equals 1. This is 0.159. StatKey also gives us options for two tails. Two tails are always going to be symmetrical. I'm going to reset the plot here because the proportions that we're actually looking at here are from the left and the right tail test that we've already done. If I reset it, click two tail again, it's going to give us the z-scores that separate the middle 95% from the outer 5% by default. But any of these numbers that are blue here, we can change. So maybe we want to find the cutoffs that separate the middle 90% from the outer 10%. We can change this to 0.90. The z-scores that separate the middle 90% from the outer 10% are plus and minus 1.645. These are the multipliers that we would use when constructing a 90% confidence interval. What if we were constructing an 85% confidence interval? We could change this number in the middle to 0.85, and this would give us our multipliers for an 85% confidence interval. It's also possible to change the proportions on the outside. Maybe we want 1% on the left and 1% on the right. StatKey automatically then changes the number in the middle to 0.980, and it gives us the z multipliers that we would use for a 98% confidence interval. You can also change the numbers at the bottom. Maybe we want to know what proportion of scores fall within a range of negative 2.5 to positive 2.5. Here we can see that 0.988 fall between z-scores of negative 2.5 and positive 2.5. I think this StatKey application is relatively easy to work with, even compared to Minitab Express. It's very easy to just click on any of these points to change them. You always need to remember, though, to pay attention to the area that is shaded in red to make sure that you do have the correct distribution. One last thing I want to show you here is if we do edit the parameters to save the parameters for an IQ test with a mean of 100, standard deviation of 15, it's the same process. So we can find any percentile. So maybe we want to find the 40th percentile. We can just find the z-score that separates the bottom 40%. Here, that would be an IQ score of 96.2. You could also change the number at the bottom to say what proportion of scores are less than an IQ score of 120. So StatKey is very easy to work with in that sense. The only downside to using StatKey compared to Minitab Express is that StatKey sometimes rounds, and in rounding, it's not going to be as precise as in Minitab Express, which gives you more decimal places. Let's go back to the PowerPoint slides now. Our second learning objective is to compute a test statistic for a normally distributed sampling distribution. This is covered in the Lock 5 textbook in section 5.1. Here's the general form of a test statistic. A test statistic is going to be equal to the sample statistic minus the null parameter divided by the standard error. This formula essentially puts our observed sample statistic on a standardized scale. We can compare this test statistic formula to the formula for a z-score. By converting our sample statistic to a test statistic, we're putting it on a distribution with a mean that is equal to the null parameter and a standard deviation that is equal to our standard error. When you conducted a randomization test in StatKey, you constructed a randomization sampling distribution that had a mean equal to the null parameter and a standard deviation equal to the standard error. We can do this because of the central limit theorem. The central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed for many frequently tested statistics. All of the statistics that we looked at so far in this course do fall into a normal distribution if the sample size is sufficiently large. So for one sample mean, one sample proportion, the difference in two means, the difference in two proportions, the slope of a simple linear regression model, and Pearson's R correlation, if the sample size is sufficiently large, then the sampling distribution will be approximately normal. Over the next few lessons, we'll examine what constitutes sufficiently large of a sample size. Essentially, it's determined by the point at which the sampling distribution becomes approximately normally distributed, and that varies depending on the parameter that we're testing. In practice, when we're constructing a confidence interval or conducting a hypothesis test, we use the normal distribution, or the t-distribution, which you'll learn about next week, as opposed to bootstrapping or randomization procedures when we're in situations where the sampling distribution is approximately normal. Let's look at a couple of examples. Here we have a randomization distribution given the null hypothesis that p equals 0.5. The original sample had a sample size of 250 with 135 successes for an observed sample proportion of 0.540. We can use our randomization distribution to find the standard error. We have our observed sample proportion, and we have our null parameter. We have all the values that we need to compute a test statistic. Our sample statistic was 0.540 minus the null parameter, which was 0.500, and that's because our null hypothesis was that p equals 0.500. And the standard error, which we got from our randomization distribution, of 0.032. First, we solve the numerator, so we find the difference between the observed sample statistic and the hypothesized parameter, and then we divide that by the standard error, giving us a test statistic of 1.25. In this case, this is a z-test statistic. In order to find our p-value now, we could construct a z-distribution, so a standard normal distribution with a mean of 0 and standard deviation of 1. And we could find our p-value by finding the area that is more extreme than z equals 1.25. We'll do more of this next week. Let's look at one more example here. This data is the body temperature data that's built into StatKey. Here we have our original sample with a sample mean of 98.26. We wanted to know if there was evidence that the population mean was different from 98.6. So we constructed a randomization distribution giving a null hypothesis of mu equals 98.6. So here we have our sample statistic, our null parameter, and our standard error that we can plug into this formula. Our sample statistic minus the null parameter divided by the standard error gives us a test statistic of negative 3.178. Next week, we'll learn that for means, we actually use a t-distribution instead of a z-distribution. But either way, this is our test statistic. We'll move on to the third learning objective now. Construct a confidence interval at any level of confidence using a normally distributed sampling distribution. This is covered in the Lock 5 textbook in section 5.2. This is the general form for a 95% confidence interval that you've been working with for a few weeks now. The sample statistic plus or minus 2 times the standard error. We saw that the 2 here is coming from the empirical rule because about 95% of the normal distribution falls within 2 standard deviations of the mean. What if we wanted to do something other than a 95% confidence interval though? We could replace that 2 with any z multiplier depending on the level of confidence that we were working with. We could find that z multiplier using Minitab Express or StatKey, doing what we did back in Learning Objective 1, where we constructed a z-distribution and we found the z-scores that separated the middle 95 or 90, 85% from the outer percent. Let's look at one example now. Construct a 90% confidence interval for the proportion of all mixed nuts that are peanuts. This is a data set that is built into StatKey if you go to bootstrap a confidence interval for a single proportion. Here we have a random sample of 100 mixed nuts. In that sample, 52 were peanuts for a sample proportion of 0.520. That 0.520 is our sample statistic. The z multiplier for a 90% confidence interval we can get using StatKey. In StatKey, I'm going to construct a normal distribution. I'm going to construct a z-distribution with a mean of 0 and a standard deviation of 1. And I need to find the z-scores that separate the middle 90% from the outer 10%. So I can change the middle value here to 0.9. The z-scores that separate the middle 90% from the outer 10% are plus and minus 1.645. These are our z multipliers for a 90% confidence interval. The standard error I can find by constructing a bootstrap sampling distribution in StatKey. I've done that here. The standard error is 0.049. Can plug all of these values into this general form of a confidence interval. Our 90% confidence interval is going to be equal to 0.520 plus or minus 1.645 times 0.049. This gives us a margin of error of 0.081 and a 90% confidence interval for the population proportion of 0.439 to 0.601. To interpret this confidence interval, I could say that I am 90% confident that the proportion of all mixed nuts that are peanuts is between 0.439 and 0.601. For our fourth learning objective, compute the mean and standard deviation of a binomial distribution. This is covered in the Lock 5 textbook in section P.4. At this point, we are finished with the normal distribution, and I'm introducing the binomial distribution. The binomial distribution is going to be used when you have one or two proportions with a small sample size. In those cases, it's inappropriate to approximate the sampling distribution with a normal distribution. In those cases, a binomial distribution is used to approximate the sampling distribution. Here's an example of that. So here we have a bootstrap dot plot for a single proportion with a relatively small sample size. We can see that the bars here are relatively far apart. So in this case, we would not approximate the sampling distribution with a normal distribution. Instead, we would use a binomial distribution. A binomial random variable is a specific type of discrete random variable that counts how often a particular event occurs in a fixed number of tries or trials. So now we're working with a discrete variable as opposed to the normal distribution, which was continuous. And if we go back to look at this plot, we can see the discrete nature of this distribution because we have these wide gaps. For a variable to be a binomial random variable, all of the following conditions must be met. There are a fixed number of trials, in other words, a fixed sample size. The probability of a success is the same on each trial, and the trials are independent of one another. Here are a few commonly used examples of binomial random variables. The number of correct guesses at 30 true-false questions when you randomly guess all answers. We have a fixed number of trials, n equals 30 because there's 30 questions on the test. The probability of a success is the same on every trial. All of the questions are true-false questions and you're randomly guessing. So the probability of getting any one question correct is 0.50. And the trials are independent of one another. Because we're randomly guessing, whether or not you get the first question right has absolutely no impact on whether or not you get any of the other questions correct. Second example, number of winning lottery tickets when you buy 10 tickets of the same kind. There are a fixed number of trials, n equals 10. The probability of success is the same on each trial because you're buying 10 of the same ticket. And the trials are independent of one another. So whether or not you win on one ticket has no impact on whether or not you win on any other tickets. Third example, number of left-handers in a randomly selected sample of 100 unrelated people. We have a fixed sample size of n equals 100. The probability of success is the same on each trial because the people are unrelated. And the trials are independent of one another, also because the people are unrelated. And finally, the number of tails when flipping a coin 10 times. There's a fixed sample size of n equals 10. The probability of a success is the same on every trial, assuming that it's a fair coin, p equals 0.50. And the trials are independent of one another, so the result on one flip does not impact the result of any other coin flip. We'll move on now to compute the mean and standard deviation of a binomial distribution. These are the formulas from your online notes. The mean, also known as the expected value, written as e of x, is mu equals n times p. So the mean is equal to the number of trials times the probability of success on any one trial. The standard deviation, or sigma, is equal to the square root of n times p times 1 minus p. Let's look at an example. Flipping a fair coin 5 times, compute the mean and standard deviation for the number of heads. The mean, or mu, is equal to n times p. N here is 5, and p is the probability of flipping heads. Given that it's a fair coin, this would be 0.5. So mu equals 5 times 0.5, which is 2.5. In other words, if we were to repeatedly flip a fair coin 5 times, record the number of heads, 5 more times, record the number of heads, and so on, the average number of heads per set of 5 flips is 2.5. The standard deviation of that distribution, or sigma, is equal to the square root of n times p times 1 minus p. In other words, the square root of 5 times 0.5 times 1 minus 0.5. This gives us the square root of 1.25, which is 1.118. So if we were to repeatedly flip a fair coin 5 times and record the number of heads, that distribution would have a mean of 2.5 and a standard deviation of 1.118. And finally, our last learning objective this week, find probabilities associated with a binomial distribution using Minitab Express. In section P.4 of the Lock 5 textbook, you'll see this formula. This is also presented in the online notes, which shows you how to find a binomial probability by hand. We'll look at 2 examples of this quickly, and then I'll get into Minitab Express to show you how you can use Minitab Express to construct a binomial distribution to find these probabilities much more quickly. In this equation, we have a few different symbols. When we say P of x equals k, what we're saying is the probability of k number of successes. The notation here is that for a combination. If you need a review of combinations, that can be found in Lesson 0 of the online notes. P then is the probability of the event of interest occurring on any one trial, in other words, the probability of success. And again, N is the number of trials. When flipping a fair coin 5 times, what is the probability of getting tails on all 5 flips? Here, N equals 5 because we're flipping the coin 5 times. K is 5 because we want to know the probability of getting 5 out of 5 flips. P, it would be 0.50 because on any one given flip, there's a 50-50 chance that you can get tails or heads. So P, that x equals 5, or the probability of getting 5 tails, is equal to 5 choose 5 times 0.5 to the power of 5 times 1 minus 0.5 to the power of 5 minus 5. If we do the math out, it gives us a probability of 0.03125. Let's look at another example. When flipping a fair coin 5 times, what is the probability of getting tails on exactly 3 flips? Again, n equals 5 because we're flipping the coin 5 times, and p still equals 0.50, but now k has changed. Here, k equals 3. P of x equals 3 is equal to 5 choose 3 times 0.5 to the power of 3 times 1 minus 0.5 to the power of 5 minus 3. Doing the math out, this gives us a probability of 0.3125. Now I'm going to take you to Minitab Express to show you how these probabilities can be found there by constructing a probability distribution plot for this binomial random variable. Again, with a blank data set, I am going to go to Statistics to construct a distribution plot. First, I'm going to show you how to construct the probability distribution with no probability shaded in and displayed. So for this example, I'll go to single distribution. The default in Minitab Express, again, is a standard normal distribution, but now we have a binomial distribution. We have 5 trials because we're flipping the coin 5 times. And on each trial, the probability of getting tails is 0.50. When we click OK, Minitab Express will give us a distribution plot for this binomial variable with n equals 5 trials and a probability of success on each trial of p equals 0.5. The nice thing about Minitab Express is that we can hover over any one of these bars and it will tell us the probability. So here we can see p, x equals 5, equals 0.03125, which is what we found when we used the formula by hand. We also found p that x equals 3 of 0.3125. Oftentimes, it's much quicker to use Minitab Express to find these probabilities than to do it all out by hand. It's also possible to use Minitab Express to find a range of probabilities on a binomial distribution. Again, I'll go to Statistics to construct a distribution plot, but now I'll show you how you can shade in a range of values. We'll display probability. We'll need to change this to a binomial variable with 5 trials and a probability of 0.50 on every one. The default is to use a specified probability, so if you want to know the top 25%, the bottom 25%, and so on, you could do that. Most of the time with binomial probabilities, though, you'll have a specified x value. So maybe I want to know the probability of having 3 or more tails out of 5. So 3 or more would be 3 and then to the right, or a right-tailed distribution. The probability of having 3 or more is 0.50. We could also find the middle range. So maybe we want to know what proportion of the time we'll get between 2 and 4 tails. And that proportion is 0.78125. You'll see this in the next few lessons when you're working with confidence intervals and hypothesis tests for 1 or 2 proportions. In cases where the sample size is relatively small and the normal approximation method is not appropriate, the binomial distribution is what is used in those cases. This concludes the full lecture video on the common distributions lesson. Again, the first 3 learning objectives that we looked at were related to the normal distribution. This is covered in section P.5 of the Lock 5 textbook. It's also reviewed and covered in section 5.1 of the Lock 5 textbook. And the last two learning objectives are related to the binomial distribution, which you'll see again in the next two lessons, and this is covered in P.4 of the Lock 5 textbook. As always, if you have any questions this week, I encourage you to post them on the discussion boards on Canvas or to drop into one of the Penn State Learning Q&A sessions.